Hello everyone, welcome to lecture 2 of my course on experimental model analysis. So, in this lecture we will continue with some more discussion on the introduction and background of experimental model analysis, and then we will talk about the lump parameter models of vibratory systems. So, there are two approaches to model analysis. One is the analytical approach. We will refer this as analytical model analysis or AMA, and other is the experimental approach, which we will refer as EMA. So, what is analytical model analysis? Analytical model analysis is based on a mathematical model of the system, which is in the form of a spatial model, right. So, it is model analysis based on a spatial model of the system. And what is spatial model? Spatial model is the description of a vibratory system in terms of mass, stiffness and damping matrices. Okay. So, it is a description of a system in terms of mass, stiffness and damping matrices, that is basically the spatial model. And what is experimental model analysis? Experimental model analysis is based on analysis of frequency response functions which are measured on the system, right. So, it is model analysis based on measured frequency response functions, which are abbreviated as FRFs. They can also be based on what are called as IRFs, the impulse response functions. Okay. And these FRFs or IRFs, they are analyzed to obtain the natural frequency, mode shapes and damping factors, right. So, it is the model analysis based on measured FRFs to identify natural frequencies, mode shapes and damping factors. The FRFs of the system, they form an equivalent description of the system and also qualify as a model of the system. So, the measured FRFs or FRFs, right, if we just say FRFs. So, the FRFs, they qualify as the model of the system referred as response model. Okay. And the identification which is done to obtain the natural frequency, motion, damping factors. These identified characteristics are called as modal characteristics, and they collectively together is also form a description of the system, and that description is called as model of the system, right. So, modal characteristics right, they form a description referred as model of the system. So, in this way you can see there are three equivalent ways to describe a dynamic system or a vibratory system. One could be spatial model, other is response model, and other is modal model. And these descriptions are equivalent descriptions. So, what is the difference between analytic experimental analysis? That can also be understood in this manner. So, let us say we have, so analytical model analysis, it starts from spatial model, right, and from the spatial analysis of the spatial model, modal model can be obtained. That is the description in terms of the natural frequency, mode shapes, and damping factors. Okay, so that is nothing but analytical model analysis. And it is also possible, if required, to obtain the response model from the modal model, and response model can also be directly obtained from the spatial model. So, this is nothing but analytical model analysis. So, in experimental model analysis, we start from the response model, because that is something obtained by measurement, the FRFs. And from this response model, the analysis of the response model gives modal model. We identify these modal characteristics which form the modal model. So, theoretically speaking, it is also possible to obtain, it should be possible to obtain the spatial model from the modal model or the response model, right. So, if I write here the spatial model, from this, right, or even from response model, it should be theoretically possible to obtain the spatial model. But as we will see later, practically it is not so feasible to obtain spatial model either from the modal model or response model, right. So, therefore, there are some practical difficulties because of which the spatial model cannot be easily obtained from modal model or response model, because of the incompleteness of the data we obtain from measurement. Because of the incompleteness of that data, the spatial model cannot be obtained from the limited data which we measure. So, this is essentially the difference between analytical model analysis and experimental model analysis. In experimental model analysis, we follow a forward path. We start from the spatial model and then go to obtain the modal model and response model. And in the experimental model analysis, we follow an inverse approach or route, in which we measure the responses and response model, from which the modal model then is derived. So, the analytical model analysis requires a model of the system, and that model can be in the form of a continuous system model or continuous model, right, is in the form of partial differential equations, okay. And for simple structures or structures with simple geometry, boundary condition, material properties, it is possible to obtain their solution, and such solutions are there. However, for complex structures which have more complex geometry, boundary conditions, material property distribution, it is very difficult, or if not impossible, to solve these partial differential equations, okay. And hence this continuous model is restricted to study of simple systems, and it is not used in for modeling or analysis of practical systems. The other approach is lump parameter model. about which we will talk more in the lecture later. And so, this model is basically gives a discrete representation of the system, right. And another approach is finite element method. Okay. So, finite element method is a technique for systematic discretization of the structure and representing the continuous system in the form of a discrete through a discrete model. So, the partial differential equations, they are converted to differential equations with only time as the variable. So, the spatial coordinates x, y, z, they are discretized, and those coordinates no longer appear as independent variables in the final equations, right. So, therefore, what we get is a discrete model of the system, right. Now, the question is whatever model is whichever method is used, right, whether it is lump parameter technique or finite element method, the model we get needs to be validated, right. It needs to be determined whether the predictions made by this model are they accurate enough or not, because then only we can use the model with confidence, right, and with reliability, right. And therefore, what is required is model validation. What is required is model validation, which basically involves determining the accuracy of the predictions made by these models, right. Therefore, model validation involves assessing the accuracy of predictions made by a model. Now, to assess the accuracy, we require the reference data against which we can compare the results of the model, right, and that reference data must be accurate. So, therefore, we require what is called as reference data, right. Reference data is required, and experimental model analysis can be used to obtain accurate model characteristics of the structure, and these estimates can be used as reference data for validation of the models, whether it is a lump parameter model or a finite element model. Okay. So, therefore, the experimental model analysis, the output can be used, and in fact it is used, right, it is used to validate spatial models. So, of course, question may arise that is the output of the experimental analysis or the data we obtain, is it accurate enough, is it accurate so that it can be used as reference data. The point is that in experimental analysis we perform the test on the structure, right, and therefore it takes into account the effects of all the geometric parameters, material parameters, boundary conditions, they all influence the results we obtain. So, if all precautions have been taken and errors are avoided in experimental analysis, then the data we get can be considered to be accurate enough and hence can be used for validation of the models, right, which is a finite element model or a lump parameter model. So, this is another important application of experimental analysis. The data of experimental analysis can also be used for finite element model updating or updating of whether it is a finite element model or a lump parameter model. So, many times some of the parameters of these models may be uncertain, and then the output of the experimental analysis, the model characteristics or FRFs, they can be used for identifying those uncertain parameters of the model through an inverse basically estimation procedure. So, this process referred as model building is another important application of experimental model analysis, right. So, model building is about inverse identification of uncertain parameters of the model. Therefore, there are many other applications of experimental model analysis. So, let us look at what are the applications of experimental model analysis. So, the first one we talked in the previous lecture is about troubleshooting of vibration and noise problems, right. That is one. We also talked about that the model test data can be used for avoidance of resonant operation, right. It can be used for model validation, it can be used for model updating, it can also be used for response simulation. So, the model characteristics we obtain or the model we obtain from experimental analysis, it can be used to simulate response of the structure to the dynamic forces which are likely to act on the system in practice. It can also be used for identification of unknown forces acting on the structure. Force identification. So, if we wish to determine that what are the forces, dynamic forces which are acting on the structure, operational forces, then by measuring frequency response functions or impulse response functions and measuring the response of the structure, operational response, it is possible to determine again through an inverse procedure the forces that are causing these responses. So, these are basically called as force identification methods. It can also be used for local structural modification studies. If we make some small changes like adding some mass or adding some stiffness or damping to the structure, right, then how the dynamic characteristics are going to change, that is something can be predicted in advance using the model of the structure, and this model identified through experimental analysis can be used for this purpose. Another application is coupled structural analysis. So, in coupled structural analysis, for example, the idea is to couple models derived from different sources. For example, in an assembly, some of the models, component models probably might be available from say finite element method, right, and for some other components maybe the experimental model analysis is being performed and model is obtained. So, in coupled structural analysis we can combine these substructure or subcomponent models to arrive at the model of the whole assembly, and because the model obtained from the experimental model analysis qualifies as a model of the system, that can be directly integrated with the other models of the some subcomponents to arrive at the complete model of the assembly. Another application is in model development, right. model development for active control. So, in active control some of the methods require a model of the structure, right, and experimental analysis can be used to derive such a model and then used in the control loop. Another application is in damage detection and structural health monitoring. Because if there is any damage occurs, right, if there is any damage in the structure or as during its service, its life, then those the damages, they change the model characteristics, and by model testing we can identify the model characteristics, and then by comparing the model characteristics at some point with the model characteristics when that system was installed, right. So, then the changes in the model characteristics can be used to determine that whether there is any damage, and if damage is there, what is the location of the damage and magnitude of damage, and that data can also be used for monitoring the health of the structure. So, these are the various applications where model testing can be used. So, now with this introduction background, we now are going to talk about what are the lump parameter models of vibratory systems, right. The theoretical basis of experimental analysis basically is based on a model of the system, right. To understand a theoretical basis, like the concepts of frequency response functions, impulse response functions, they are all defined based on a spatial model of the system, and hence we are going to talk about say lump parameter model of a vibratory system. So, lump parameter model is a representation of a system using discrete physical elements, right. Let us say representation of the system using discrete physical elements. But then the question arises, what kind of physical elements are to be used to represent the or to make the model of a vibratory system. So, what are the elements of the model? So, what are the, we can raise the question that what are the physical characteristics or parameters of the system which affect the vibratory phenomena. So, one parameter which affects is the inertia or mass of the parameter, right, mass of the system. So, the mass of the system and its distribution of the mass, right, that affects the vibration characteristics, right, it affects how the system vibrates. So, therefore, we need to represent this mass in the model, right. The other characteristics is the ability of the system to restore to its mean position, right. When the system is displaced, the system tends to apply forces of restoration, elastic forces due to the elasticity of the system, so that the system is restored to its mean position. So, it means the elasticity of the system is another characteristics or physical property that needs to be modeled, right. Elasticity, which basically amounts to the gives rise to the stiffness of the system, right. Stiffness is the force per unit deflection, right. So, this property this quantity is basically captures the elastic property of the system. So, it means we need to describe the mass, we need to describe the stiffness represented by K, right. Is there any other property which is required to be specified? So, a model which is based on representing the mass and stiffness, right, is called an undamped model. Right. The description in terms of mass and stiffness. Okay. It could be more number of, it could be, you know, in terms of masses and stiffnesses, if there are more number of masses and stiffness being used to represent the system. But we see that in practice, you know, the vibration, for example, if a system is disturbed, then the system vibration decays with time, right. If under the free vibration, the system vibration decays with time. So that points to existence of some dissipative forces in the system. The undamped model you know, in terms of mass and stiffness, it does not have ability to represent the dissipative nature of the system, right. So, so in fact the mass basically represents the ability of the system to store kinetic energy. Stiffness represents ability of the system to store potential or strain energy. So, if a system is deflected, is deformed, then it stores energy, right, because of the deformation. And if the forces causing deflection are removed, then that energy causes the system, you know, to go back to its you know, mean position, right. So, these therefore, the system has ability to store energy either as a kinetic energy or potential energy, but then system also has ability or you know, has forces by which this energy is dissipated. So, if the decaying nature of the vibration of the free vibration of a system is to be modeled, then we also need to model those dissipative forces, and this is done using a viscous damper, right. So, dissipation of energy also needs to be modeled, and this is modeled using a damper or damping element. So, therefore, we need to model the mass, stiffness and damping characteristics. To arrive at a model of the system. In fact, these are the three elements which make that description complete. The other parameters, for example, let us say what about the temperature effect, how that is, you know, captured by these characteristics. So, if there is a change in temperature, then the stiffness or damping characteristics may be affected, and that therefore, the temperature parameter is indirectly captured by the stiffness and damping elements. So, therefore, the mass, stiffness and damping needs to be modeled for arriving at a description of the system, right. Now, what is lump parameter representation? What is lump parameter model? In lump parameter model, we represent the mass, stiffness and damping characteristics by discrete idealized elements. Every practical system is continuous in nature, right, because it has these characteristics you know, presented in distributed form. A system has its mass or inertia continuously distributed throughout its physical domain. Similarly, the elastic property, you know, the forces due to elasticity, they arise in all the, you know, at all the points in the system. Similarly, the energy dissipation may occur in different, you throughout the domain of the system. So, therefore, these properties are distributed continuously, and representing them by idealized elements, lumped elements basically gives us a lump parameter model. And in what sense they are lumped? The properties which are being represented in the lump parameter model, they are mutually exclusive, right. So, in this we represent the mass of the system by a rigid mass like this, okay. We represent the stiffness by a spring element like this with stiffness K, and we represent the damping characteristics of the system using a viscous damper. So, often we use a viscous damper because it offers ease in the mathematical analysis of the model. So, this is a viscous damper. So, these elements, they are basically are called lumped elements, and the reason they are called lumped is because of the fact that the properties they possess, those properties are mutually exclusive properties, which means the mass, rigid mass has only mass and it does not have any stiffness or damping. Spring has only stiffness, or it provides only elastic force, but it does not have any mass or it does not have any damping effect. Similarly, the viscous damper has only damping effect, it provides only a damping force, but does not basically have any mass or stiffness. So, in that sense these are lumped and these are idealized, right, because in real world if you have a spring, it will also have some, in addition to stiffness, it will also have some mass and some damping inside it. So, but for sake of making this model, these are basically taken as lumped idealized elements. So, therefore, in lump parameter model we represent a system by a collection of these masses, stiffnesses and dampers, right. So, let us take an example to understand what is lump parameter model and how we can arrive at lump parameter model of a system. Let us take example of a car moving on a let me take example of a car moving on a rough road like this. So, this car is moving like this. So, what is going to happen when the car moves? There would be forces of the dynamic forces would come. The dynamic forces may come from engine and transmission line excitation, right. They may also come because of the excitation may also come from the ground because of the road roughness, right. Excitation due to road irregularities. So, what do they do? These excitations, they basically excite the the body of the system, body of the car, and causes its vibration, right. And then so one of the undesirable effect is that it leads to a reduced ride comfort, right. It leads to reduced ride comfort of the passengers, and therefore this could be one motivation for building the a model of the car, so that we can study the dynamic behavior of the car. How does it vibrate, right? What is its dynamic response under the action of these excitation forces. So, let us say we want to study what is the bouncing motion of the car. So, when these excitations appear, how the car vibrates in the vertical direction. Let us say that is our objective, right. So, let us say we want to study what is the bouncing motion of the car, right. So, a straightforward approach to study this could be to represent the mass of the car as a rigid mass like this m. So, this represents the mass of the whole car, because that is the mass which is a sprung mass, it is going to vibrate, right. And then we can represent the stiffness of the car. The stiffness, the bouncing motion primarily occurs because of the flexible suspension and flexibility of the tires. So, we can combine the stiffness as a first approximation, we can combine the stiffness of the tire and the stiffness of the suspension as the two stiffnesses in series and obtain the equivalent stiffness, and represent that stiffness by a spring element like this. And then we also have some damping, right, because there would be some loss of energy when the tire flexes and when the suspension deforms. So, there would be some energy loss. So, that energy loss we can represent it by a viscous damper like this, right. And then this basically moves on a road like this. So, then we have this road like here. So, therefore, here we have the excitation or the vertical displacement because of the car, because of the road irregularities, let us say represented by y of t. So, that causes the displacement x of t, and of course, in addition we also have the forces acting due to the engine and transmission line, if represented by f of t, correct. So, therefore, this gives us now a physical equivalent model of the car on the rough road, okay, where we have represented the mass, stiffness and damping characteristics of the car, and then we can further analyze this model to determine that what is x, right, what is x if y of t is given and if f of t is given. So, it should be possible for us to determine that. Now, in this case, this particular model, if we see that it captures or it describes the system bouncing motion by one coordinate, right, x of t, right. So, to describe the displacement of the car using this model, we require only one coordinate to prescribe the displaced configuration, right, and hence the degree of freedom of this model is 1. So, what is degree of freedom? Degree of freedom is the number of independent coordinates required to specify the displaced configuration of the system. So, in this case, based on this model, we require only one coordinate x of t to describe the displaced configuration of this model, and hence this model is basically a single degree of freedom model, which is abbreviated as SDOF, right, that is single DOF model, and degree of freedom also we will like to abbreviate as DOF. So, this is I think one model we got, right. So, we can call it say 1. Let us suppose that we want to improve the accuracy of the representation, right. For example, one motivation for that could be we notice that the body of the car and the wheel, they are going to have distinct motions in the vertical direction, because the tire is flexible, right, and therefore it is going to undergo deformation, right, and then the because there is suspension between the body and the wheel, the displacement of the body in general would be different than that of the wheel of the car, and hence in order to have a better representation of the stiffness and mass characteristics, we can build a better model. So let us say we represent the mass of the body above the suspension as, let us say, m1, and if we describe the stiffness characteristics of the suspension by a spring with K1 and the damping characteristics of the suspension by C1, and now we separately represent the mass of the tire, right. So, if we represent that mass as mass m2 and the stiffness of the tire as K2 and damping of the tire as C2, right. So, that is another representation possible of the LM parameter representation possible. So, in this case we have the y of t is the excitation coming from the ground and f of t is the force acting on the body of the car, and then we have this as 1 degree of freedom, right, because that is the displacement of the car body, and the displacement of the wheel is going to be different, right, is therefore that will be represented by x2. So, here m2 contains the all the masses of all the 4 wheels, right. Similarly, K2 and C2, they represent the equivalent stiffness of the suspension, right, and damping of the suspension at all the 4 wheels, right. Now, in this case we see that it is there are 2 degrees of freedom, right, degree of freedom 1, degree of freedom 2. So, therefore, it is a 2 DOF model. Okay. So, this model more accurately represents the distribution of mass, stiffness and damping in the system. Let us say our objective is not only to study the bouncing motion, but also the pitching motion of the car. Pitching motion is the slope of the car in the vertical plane, right. Okay. So, that is the pitching motion. So, so therefore, for that now we will have to represent the stiffness and damping characteristics of the front tires and rear tires separately, because then only the pitching motion can be captured. In the previous 2 models, the body was represented by a single lump mass. So, so it was basically a point mass essentially. So, it cannot capture the slope of the car, or it cannot capture the pitching motion. So, therefore, what we do is that we represent the car with a body of mass m1 and moment of inertia I, right, about the axis which is perpendicular to the plane of this paper, right. And then we have the stiffness of the front tires of the front suspension and damping of the front suspension, equivalent damping, right. And let us represent this by Kf1 and Cf1, right, and let us say this is the mass of the front tires, it is m2, and then we have the damping of the tires and the stiffness of the tires, right, and So, let us say this is the KF2 and CF2, right, and similarly for the rear we have this stiffness and damping of the rear suspension. Let us call it as KR1 and CR1, and the stiffness and damping of the rear tires. So, KR2 and CR2, and then we have the both tire moving on the rough road. So, in this case what we note, we have now excitation from the ground as before, and we have the engine forces, right, and if there are any torques or couples acting, that also can be accounted for. Then we have now the vertical motion, the bouncing motion of the car, sorry, this is x1, and then we also have the pitching motion theta, right. So, that is another degree of freedom, and then we have the vertical motion of the front tire, which we can call as x2, and the vertical motion of the rear tire x3. So, you can see if we are trying to predict the bouncing and pitching motion, right. So, to predict bouncing and pitching motion, now we have a 4 degree of freedom model, right. We have 4 degree of freedom model where x1, x2, x3 and theta, these are the 4 degrees of freedom. Similarly, if our objective is to also predict the rolling motion, right. So, if we want to predict bouncing, pitching as well as rolling motion. So, rolling motion is the rotation of the car body about the about an axis, right, which is aligned with the direction of the movement, right. So, then in that now case we will have to take into account the distance between the left and right pairs of tires, because that distance is going to affect the rolling motion. And therefore, if I try to sketch the figure, make a 3-dimensional figure like this, that is nothing but the car body, right, and then we will have the 2 tires on the front side shown by these rigid masses like this, and then we have tires on the rear side shown by these 2 rigid masses, right, and then of course we will have the suspensions, right. So, the spring and dashpot, spring and dashpot, right, and then we have this spring and dashpot for the tires, right, spring and dashpot for the similarly here. So, so therefore, we have this is 1 degree of freedom x1, then we have the rotation of the car body in the vertical plane, right, like this, the vertical plane which contains the direction of movement of the car, that is theta, right, and then the angle of the slope of the car in the direction in a plane which is perpendicular to direction of movement, let us say that is phi, that is rolling motion, right, and then we have these vertical motions of the tires, right, like this. So x1, so if I call this x2, x3, x4, x5, correct. So in this way you can see we have the degrees of freedom, we have now 3 plus 4, that is 7 degree of model, let us say 7 DOF model, where x1 is the bouncing motion, then we have the pitching motion theta, then we have the rolling motion phi, and then we have the x2, x3, x4, x5 as the vertical displacement of the 4 tires. So this is another model. So this also is a lump parameter model, right. So this is a fourth model. And then other question arises that what is the role of the body of the car, because that also is flexible and that also is modes of vibration. How that can be accounted? Now accounting the modeling the body of the car through lump parameter model is a little difficult task, because there are no obvious choices for the representing the body through a collection of masses, springs and dampers, and we require a more systematic approach, like for example finite element method provides that approach, where we can discretize the body also and represent it through mass, stiffness and damping elements, which leads to basically mass, stiffness and damping matrices. So that will give us another discrete model just like these models. So therefore the important thing to note here is that the models we are getting as we demand or as we represent the system more closely, more accurately by collection of masses, stiffness and dampers, the accuracy of representation improves, right. So the accuracy improves, but the effort required to solve the model will also proportionately go up, right. Therefore we see that model accuracy and computational effort they have a trade off. Between them, right. As the accuracy goes up, the computational effort also goes up, right. So therefore improvement in accuracy is desirable, but improvement in increase in computational effort is not desirable. So that has to be kept in mind. The other thing is that the the model is not unique. That is another important thing to note, because we saw that depending upon the purpose and accuracy right that is required, we can make different models, right. As the purpose changed, a different model was required and could be made. So therefore a model is just one of the models of the system, and it is not a unique representation of the structure, right. So the physical structure of system is unique, but the model we have made is not unique. There can be multiple representations of of the same structure. So in this way we have completed our discussion on the lump parameter model, and we can stop here, and in the next class we will talk about now the further how the equations of motion can be obtained for these systems, right. So thank you.